Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're joking here about the title of Tony's talk. I had the pleasure of having Tony join me for a trip to South America earlier this year to present a showcase some of the RFP work that was being done to an audience of academics there. And as with many of you, over the course of the time of your RFP, the focus of your work is refined a bit, so the title of your talk becomes a bit more refined than the title you may have used for your RFP proposal. So I was joking with Tony that perhaps to allow him to do stepwise refinement and retain an air of mystery and revelation, the title on the talk here should just be Stuff, and then he could work towards a more specific definition. But the title on the program is Transactional Persistent Managed Runtime Environments. Tony received the Bachelor of Science degree in Mathematical Sciences from the University of Adelaide in Australia in 1985, Masters of Science in CS from Waikato in New Zealand in 87, and continued on to earn the PhD in 1995 from the University of Massachusetts. And in 1995, Tony was appointed to the faculty of Purdue University in the Department of CS, where he now holds the rank of Associate Professor. His work is in the area of implementing programming language, programming language design and implementation, with specific interest in database and persistent programming languages, object-oriented database systems, dynamic memory management, compiler optimization, and architectural support for programming languages and applications. Tony.
Thanks, Mark. Yeah, so this is a bit of a mishmash title, although I will be zooming in on a couple of the items here as we go. I should point out that much of what I will be talking about today is work by a PhD student of mine, Adam Weltz, who has just yesterday accepted a position at Intel Labs, despite the fact that he still has a dissertation to write. But that's indicative, I think, of the he's not going until 2006. That's indicative of the interest, I think, or the intense interest in the work that he's been doing on transactional memory, software transactional memory, and particularly also questions of how hardware might support software transactional memory. It's also work that's being done with a colleague of mine, Suresh Jagannathan. So the main thrust of this talk will be about exploiting parallelism, and in particular thread-level parallelism, especially given that today's hardware trends represent adaptation in the face of failure. It's an interesting way to put it, I suppose, but adaptation in the face of failure to scale processor speeds. And so hardware manufacturers are having to come up with other ways of using chip real estate. Actually, it's not just processor speeds, it's also controlling heat and so on as well. Using chip real estate and using techniques such as simultaneous multi-threading, sometimes called hyper-threading, trademark, or chip multiprocessing, sometimes called multi-core processors. And these trends are pointing out the need to exploit through the thread-level parallelism available in our programs, but where we are faced with the current standard programming model for threads based on synchronization using mutual exclusion locks. And this is sort of a problem because they have some nasty properties that can arise. Things like deadlock and priority inversion can occur. And also they force an inherently serial execution, which is something we may not want to be locked into, pardon the pun, with these threaded processes. So the question is, can we do better? And this is not a new idea, of course. Transactions are as old as the hills, and certainly the database community for managing concurrency. But the question here is, can transactions actually come to some rescue in the face of this parallelism? So I just want to point out a few items of work here. We've done some work on revocable locks, looking at how we can use undoing of the effects of threads that may be executing at low priority, which are forced to revoke in the presence of higher priority threads coming in and trying to acquire a lock. This is a technique that allows us to eliminate priority inversion. Transactional monitors is what I'm going to be focusing on today, where we're looking at the concurrent execution of lock scopes to improve performance and scalability, while preserving, at least for the programmer, the serial view of execution, which is a nice model to program against, and also which permits us to have freedom from deadlock and things like priority inversion as well. And finally, there's a later piece of work that is looking at how we can make existing serial programs execute more parallel by exploiting the notion of futures. It's a feature that's been talked about in the functional programming community for many years, but taking that and putting it into the context of a language like C# or Java by looking at executing asynchronous function calls in parallel and then just making sure that those asynchronous calls preserve the semantics of function call even though they happen to be executing in parallel. Again, I'll be focusing on this transactional monitors work just to give you a sense of the flavor of what we're doing. There's a lot more details there, and you can look at the papers that I've noted on the previous slide. Okay, so the usual thing with mutual exclusion, I'm going to adopt an example here based on a pair of linked bank accounts, a checking account and a savings account, say, which are declared as an account with a balance, and where we have some functionality that allows us to transfer funds from one account to another, and of course to preserve the meaning of the transfer, we have to have the actual transfer operations from one account to the other appear to occur atomically. So usual strategy is to use a locking strategy, and the usual sorts of things happen. We acquire a lock. A thread acquires a lock as it tries to transfer funds from one account to another. It enters the region of the lock, does the transfer from, or at least debits the checking account, and goes on to, at that point may continue on at some point to access the savings account. But, of course, there's, in the presence of concurrency, the likelihood of another thread coming along and asking, well, what's the balance of the accounts? And in doing so, we'll try to acquire the lock, and, of course, is forced to wait while the other thread goes on and does the modification of the savings account. Now, this gives us the usual sorts of serial execution that one would expect for preserving the atomicity of the operation that is the transfer operation. Okay, so we're imposing serial execution here. Locking, that's what locking does. But of course, that constrains concurrency, may reduce parallel throughput. It also can put more burden on the programmer to be careful about where they place locks if they want their programs to scale on parallel systems, and also for robustness if they want to avoid problems like deadlock. So there are programming pitfalls here, which we're also addressing, not just performance pitfalls, in that there's complicated composability when you have lock schemes, and of the other things of deadlock and priority inversion. So what are transactional monitors? These are an approach where we're going to allow the concurrent execution of the lock scopes in order to improve performance and scalability. Once again, though, we will still preserve the serial view with the notion of serialisability. That's a long-standing notion of correctness, again, drawn from the database community. Our transactional monitors will be obstruction-free, free of deadlock and priority inversion, and so can be more promoting of composition of code. We're particularly going to be targeting applications that exhibit contention for locks. Clearly, if you have a lock that's uncontended, then there is no concurrency to be exploited. Now, we actually have an implementation of a prototype transactional monitors framework based on techniques of optimistic lightweight transactions. We're going to be tracking accesses by different threads to shared data, and we're going to track those accesses in a way that allows us to ensure serializability by rolling back threads that violate the serializability properties. And I'm going to be talking about two particular schemes here. One's a low-contention scheme that we've devised, which is intended to function with low overhead to the executing threads, but where there is a high degree of inaccuracy in the detection of conflict. So you may actually result in conflicts being detected when there were none, but this is at the price of speed. We're also going to look at another scheme, which is a high-contention scheme, where there is additional overhead to the executing threads, but where the accuracy of conflict detection is much higher, and so presumably we can be successful more often in executing our transactions. Now, I'll note here that this prototype implementation is based on the JIKES RVM for now, not Rotor. Much of what our motivation for that is arising out of our needs to do performance experiments. I think we sort of talked a little bit about that yesterday and how Rotor may be evolving to a situation where that will be more flexible for us. And also because of the portability of JIKES to the various sorts of SMPs that we had lying around the place, tending to be running Linux and so on. So we wanted to be able to run on platforms that we had available. Okay, so the low contention scheme operates by assuming that there are very few concurrent writes, and it's really just a race. The first thread to write will win, and any thread that tries to execute within a lock scope, within a monitor scope, that sees that another thread is written will lose. So any write will trigger conflict. Whether or not that write is to data that both threads have read or not is another question. We need to have, in this case then, some overhead on every write to objects in the heap. So we have to have what's known as a write barrier to detect the conflicts. But we do not have any need to monitor accesses that are only reading objects in the heap. And we will not do any logging. So there's no logging of the updates that have been performed. We're just keeping track of a very small amount of information. So here's the example with the accounts set up again. What we have here is a thread T prime that's about to enter a monitored region to perform the transfer. Here it goes. We get in there. But another thread comes along and also tries to enter the monitored region, and we have no problem with that. We let it enter. Now, you notice here we're maintaining some information about how many threads happen to be in the region. So in this case, every time those threads entered, the count was incremented. The first thread will then go ahead to try and write the checking account object to deduct the balance. To deduct the amount being transferred from the balance. And at that point, we'll say, I'm the writer for this particular monitored region. And so, in effect, I'm going to be the winner of this race. The other thread will come along. It may choose to access things concurrently. But at the point where it's going to execute that monitored region, it will do a check to see whether there is any other thread that has written to objects within that region. And if any writes have occurred, then it will be revoked. It'll have to go back and start again. So we have to unwind everything back to the entry point to the monitored region, and that thread then has to start its execution. And this will ensure consistency. Last thread out will last thread out of the region will clear the writer field and decrement the count back to 0 so that we can continue. So it's sort of like last thread turns the lights out. Okay, so that's the low contention scheme. The high contention scheme is one that's intended to tolerate multiple writers. And the intention here is that if we have two threads writing that perform writes that do not conflict, then they will both succeed. So what we need is more accurate conflict detection. And we're going to keep actually specific information about the subset of objects that may have been read or written. This is not going to be precise. It'll be somewhat imprecise, but still give us a mechanism to divide or separate writes to distinct objects or regions. And we're also going to maintain a global write map recording parts of the heap that have been modified. So this needs us to implement both read and write barriers. Every access has to have some overhead added to it. So there's additional overhead in this scheme that we're going to hope to win back by improved concurrency. And we're going to also have to version objects in order to be able to roll back the writes that revoked threads may have performed. So how does this work? We've got here this local read and local write map for each thread. There's a global write map here. The maps are effectively hashed on the objects. Morning, Ben. And here we have the first thread coming in to deduct the transfer amount from the checking balance. And this deduction or this write is recorded by setting a field in the local write map for that thread. The other thread comes along and says, OK, well, I'm trying to figure out the total balance of the checking and savings accounts, and attempts to read from the checking account, and sets a region in its local, a bit in its local read map to indicate that it has read from that object C. The other thread then proceeds to do the update to the savings account balance, sets a bit in its local write map to record that fact, and at the time that it then exits the monitor, takes the information about what objects it's written to and installs them in the global write map. So this is effectively posting a claim on those writes to those objects that will have to be respected by other threads. So the other thread comes along and eventually reads the savings account balance in order to get the total balance. And then at exit, it's going to ask the question, have I seen anything that could potentially be inconsistent? And in this case, because there is overlap between the local read set and the global write set, we're going to say, no, you cannot complete. You have to go back. You may have seen inconsistent state. Roll back and restart. OK, so that's the fundamental schemes that we've implemented. We've actually run these on our prototype with a synthetic benchmark that we've devised, which is intended to not necessarily be a realistic reflection of real applications, but which has a bunch of different knobs that we can turn to control how much contention there might be, what the ratio of reads and writes might be, how fine-grained or how coarse-grained the lock regions, the monitored regions might be, and so on. So 007 is a database benchmark. It has a design hierarchy of parts for some sort of abstract engineering database. The part hierarchy is multi-level. What we've done is we've synchronized at various levels within that part hierarchy, and we've also written it such that we can do a mix of both read and write traversals of various mixes of reads and writes. And we're going to be looking at configurations of 8 threads running on a single processor, or 64 threads running on 8 processors, and varying those parameters. And we're going to be looking also at the average of what we call hot traversals. These are traversals over, repeated traversals over the design database, where we're avoiding any JIT compilation in the background, so that the hot traversals refer to the fact that we actually really are running at full speed. OK, so what have we got here? We've got a graph here now of the results for the low-contention scheme. Now remember, this is a scheme that is very inaccurate about effectively it's just a race. Whoever does the first write wins, and so there's likelihood that if there is a lot of contention, then you've got a lot of losers. But in the case that there's low contention, presumably we're going to perhaps have a win. So what have we got? We've got elapsed time for execution. It's normalized to a situation where we have a single transaction executing, so there's no contention. Actually, no, it's normalized to the case where we have just regular locking, actually. So what we're trying to do is show that we can get improvements in speed by increasing concurrency. So anything that falls below this dashed line indicates a win for us. So clearly, in some circumstances here, we're not winning. We've got elapsed time normalized to standard locks. In the cases where we have large numbers of threads with, now this blue line corresponds to the case where we have 90% of the accesses are writes, 10% are reads. So this is a very high contention case where we would expect to lose. The low contention scheme is not designed for that situation, so clearly performance is way worse. But in the cases here where we have 90% of accesses reads and 10% writes, we are getting an improvement in throughput, parallel throughput there over the case with the single lock, with the over the locking approach, as the number of threads vary. So we're getting consistent speed ups there. This graph shows shows the variance that you get when you have coarse versus fine-grained locking. So locking at level 1 says lock at the root object of the hierarchy, and locking at level 6 is way down in the small little parts that make up that hierarchy. And so we're looking here now at granularity as we vary the percentage of writes from 10% up to 90%. And things to note here are that when things are very coarse-grained, of course, we lose in the low contention scheme because there's more likelihood that someone else will write while we're actually executing. But the finer-grained schemes where there's a less likelihood that another thread's going to come into the lock region, we are at least closer to the line, but of course we're still losing here, except for very low write ratios down here at this end. Okay. Here are the results for the high-contention scheme. Now, once again, what this is intended to show is that as we increase contention, we would like to, of course, get better performance because we're able to take advantage of the fact that multiple threads are trying to enter the same lock region, and we're going to be able to get the parallelism out because we're going to let them all run at the same time. So again, here, the blue line is the high contention case where you have 90% writes, so most of the time we're losing there. But you'll see that for the other schemes where it's moderate degrees of write, then we are getting a win at the high concurrency settings. Of course, down this end, we see the overheads of this high contention scheme, which I said, as I said earlier, has extra support, has to have extra overhead at every access to track both reads and writes. And then this once again looks at the granularity issues. So I'll just skip through that. Okay, so what can we conclude about these transactional monitors? First of all, they do appear to, in certain circumstances, for certain workloads, increase concurrency and potential throughput. Now, this is indicative of the fact that it might be actually useful to have some sort of hybrid setup in your system where sometimes when there's low contention, you don't even have to switch into a transactional mode. You might just run with locks, regular old mutual exclusion locks. But in cases where contention is detected and one wants to take advantage of possible potential concurrency that's there, we can use the transactional approach to increase that concurrency and the potential throughput of the system. The results indicate that we get relatively good performance in certain areas of that space. So again, you know, there is incentive to switch to transactional execution in certain regions of the workload space. We saw that we get scalability in different circumstances for both the low contention and high contention schemes. And we get, you know, up to 5 times speed ups in certain instances across the contention ranges. Okay, so what are the implications of this for Rotor and the CLI? Well, I will note that, first of all, that we've built our system on top of the memory management toolkit that's been done by Steve Blackburn in Australia, which has been ported to Rotor by his group. So they actually completed that port sometime, I guess, in the last year, 6 months or so maybe. We've taken MMTK and extended it with object versioning. So we have a bunch of infrastructure here that we could potentially port into Rotor based on this MMTK implementation. I'll also go on to say that the thing about locks is that they're actually a very low-level managed runtime component. That locking is inherent in these sorts of runtimes and is provided to multiple languages. So what we really are interested in is how we can do this revocation and transaction stuff as a plug-and-play replacement for standard locking. What circumstances can we switch over to a transaction-based execution versus a locking execution? And if we can do that, then this facility will be available, of course, to all the languages that are running on CLI if they are using locking. And of course, there is a lot of activity, not just here at Microsoft, but at Intel and various other places, looking at transactional executions, software transactional memory. I know Tim Harris at MSR Cambridge is leading a big effort there. We are actually doing some other things that are sort of Rotor-related, CLI-related, looking at some compiler analyses to eliminate the sorts of barriers that we see in these transactional systems, doing escape-style analysis. That's work that my colleague Suresh is hooking into with the Phoenix program. And also in background, I've got an interest in a language called Module 3. It's more obscure these days than it used to be, but it had some influence at some points. But the particular interest for me is that I have a version of Module 3 that has both transactions and persistence in that language, implemented for that language. And so we're actually doing a retarget of the backend to MSIL. This has meant adjusting a bunch of the implementation decisions in the original Module 3 compiler and runtime. For example, we're having to switch over to native threads because we want to be able to take advantage of the underlying CLI threading and its potential for multiprocessors. and also modifications of the previously extant incremental and generational garbage collector that's in that system, which was based on using page protection barriers to deal with incrementality and generational execution. And we're replacing those with software barriers so that once again we can get into this setting of multiple threads running in parallel. Right now, mostly we're running we're designing for unmanaged execution because the runtime for Module 3 is so heavily implemented in Module 3 as part of its own sort of separate runtime system. But looking at migrating how we can migrate those to the CLI-based support. And that's where I'll stop. Questions? Yes?
What Module 3 compiler are you using as a basis for porting to CLI? And are you going to use
sorry? The critical mass Module 3 compiler.
And are you going to use Phoenix for Module implementation?
Well, it would be nice to, okay, so it would be nice to be able to get into Phoenix to be able to take advantage of analyses and optimizations that we would like to have take place, like some of these barrier things. So right now with this transactions work, the barriers are there on every single axis. We have no optimization taking place where we can say, oh, I know I've already done a write to this object. I don't need to execute the barrier code. So certainly Phoenix, I think, is going to be a great opportunity. I really think that there's going to be some fun to be had there. That must have been a tricky one.
No, I'm interested in whether you've thought about how to do structural compatibility of types in a managed way.
Oh, with Module 3?
Yeah.
Yeah, a little bit.
Okay. Well, I will take it off.
I actually would like to talk to you about that too. Yeah.
Okay.